Hi everybody. As always, this talk is based on our meetup. The link is down below in the comments. Please feel free to share, like, subscribe, join us. We meet bi-monthly to discuss things that we or other people have seen in production which are related to AI ML. Myself, I am Jonathan Yarconi. I recently spent 6 years at Google leading the AI and ML. In the past year, together with my co-founder Guy, we founded Latent AI, and together with our team, we take on AI ML projects across the spectrum. In this session, we'll be breaking down the cost of LLMs, and as always, it's based on what we're seeing with customers in production. So a bit about the agenda. The agenda will be split into three, where initially we will be discussing the cost components very briefly. Then the bulk of the time will be spent on optimization methods. And last but not least, we'll have demos which will be kind of spread out throughout the lecture. And as always, I will also share the link to the demos in the comments below. So feel free to take them, reuse them. We encourage it. I want to make sure that everybody's on the same page before we begin, because a lot of these words are obviously used interchangeably. When somebody is saying that they're giving a sentence to an LLM or an input or a prompt or a query context, essentially the words which are given to the LLM are tokens. So the working assumption of this talk is that you are familiar with LLMs and that you're aware of the general concepts such as tokenization, chunking, and RAG. It's not strictly relevant, but I kind of start from that point because I assume people who want to optimize costs have already kind of used LLM to some extent. When we look at the different cost components of running LLMs in production, these are the main four ones. Then we have first and foremost, the prompts, which include the input and the output. Infrastructure. This can be either the infrastructure of the training or the serving. In the case of LLMs, it could be self-hosted models, or it can be the cost of fine-tuning the models. Then we have the growing list of tools. Yes, currently most of them are free, but it is to be expected that over time, some of these tools will start charging in some way. A few examples of these tools would be Prompt IDE, data quality platform, LLM gateways, vector databases, and monitoring platforms. Last but not least, we always have the human component, at least until AGI will take over, and that is the cost of developing the system, designing the system, maintaining the system, and so on and so forth. Now, I want to break down these components into their respective use cases in production. The following diagram kind of shows the different production types. So when you're starting out, you're probably using GPT-4 and you're running at a low scale. Later down the line, you're going to want to increase that scale. And there's also always the option of self-hosted models. Now I put a dollar sign to kind of give you the respective the relative cost. Each one of them is per the scenario. So when you're running at low scale, the cost of the prompts themselves is not the majority of the cost. If you're testing the system and you're doing it manually, if you're running just in a small cohort of users, that's not the huge cost. Tools, I don't put this at zero on any of these scenarios because, again, I assume some of them are going to cost and maybe some of them are going to cost in relation to your usage, but currently let's assume it's not zero. And human, when you're running at low scale and there's basically no cost other than the human cost, and relatively speaking, it is the most expensive one. Then we graduate onto a high scale. This is once you're scaling the system, using a lot of users, using a lot of prompts, and the cost here starts to ramp up. We'll talk in the next slide a bit about some cost examples of different models, but at this point, the majority of your spend is going on prompt. There's no infrastructure cost because we're talking about using a third-party provider such as OpenAI, so they'll be hosting the model. Tools, the same applies as before, and now humans has shrunk in cost, not because we're using cheaper personnel, but simply because, relatively speaking, the prompt is the majority of the cost. Last but not least, we have to address the self-hosted version. There are a lot of reasons why to run self-hosted. Privacy, security being the chief one. A lot of the times it's also a cost constraint. You can take one of the open source models and run it locally, and at the end of the day it equates to less money. Here prompts is zero because you're not paying a third-party provider. You're mostly going to incur in correlation to your infrastructure costs, so it's not priced the same way. The underlying infrastructure is what costs, and it depends on what spec you have under it. Tools remains the same, and human, again, the cost kind of rises because in relation you're now paying mostly for infrastructure and human costs. There's a lot that can be done, and you're here, so you're probably familiar with the common method of paying for LLMs. We pay by the number of tokens that we send. Therefore, a couple of vague strategies on how to reduce the cost are listed here below. If we're paying by the token, we can send less tokens. We can remove unnecessary information or fluff. This can be both in the realm of unnecessary information that might not be adding to the problem that we're trying to solve. And it can also be things such as propositions and things such as and additional spaces. Not always, as I was asked recently, and as I'll show in the next example. When we're doing code, spaces are relevant, but when we're writing text, and if suddenly we have 3 to 4 lines spaces in between 2 paragraphs, it doesn't really convey a lot of meaning, and it's probably not necessary, so we can just remove it. Another one is don't send the tokens. This can obviously relate to not sending it to a third-party provider and opting for a self-hosted model, and we'll talk about other options in a couple of moments. And last but not least, send it to cheaper models. So on the right, you can see a small table comparing different models. GPT-4 currently is the most expensive method. It's priced differently per input and output tokens. I just averaged 50-50. It's 60-30 for input and 60 for output. I just averaged it out. But in reality, you're probably going to weigh it different if you're calculating, because normally the input is around 1 order of magnitude larger than the output. GPT-4, $45 for 1 million tokens. Just to put this in perspective, the entire Holy Bible is around 500,000 tokens. Okay, so if you were to send the entire Bible to GPT-4 and ask it a question about the Bible, you would be paying around $100, which is not a small amount, but just think what capability you're getting. You get the ability to ask any question about whatever in the Bible in one request, and it's going to cost you $100. Now, given, as some of you know, currently you can't, there's no context window, which is a million tokens long, but I expect there to be in the future. And also, we're just talking about the relative cost and capabilities here. Next up is GPT 3.5 fine-tuned. This is a great alternative. There are quite a number of papers detailing how with a fine-tuned 3.5 you can actually beat the performance of GPT-4 on certain tasks. This is already 11% of the cost of GPT-4. If I go one step further, non-fine-tuned 3.5 turbo, it's already 3% of the cost of GPT-4. If I go even one step further and I use Mistral 7B, which given is not as a performant model, but a relatively good one, both in terms of performance, latency, and cost, that's already 0.5% of what it would cost to do the same with GPT-4. And if I use additional methods such as compression of the prompt, I'm already 0.02 the cost of GPT-4, which is 3 orders of magnitude cost reduction. Now, matters. I wouldn't invest a lot of time, but I wanted to show you how and why why tokenization matters. At the end of the day, you're paying per token, and different tokenizers translate different words into different amount of tokens. Specific models may work different on different tasks. A few good examples would be languages. Models which are trained on certain languages tend to tokenize those languages in a better way. Here you can see that GPT-4 tokenizes code much better than GPT-2. GPT-2 takes different spaces as different tokens, and the same piece of text here is worth almost double the tokens. Now, there are reasons for that, byte pair encoding, which I won't go into that, but generally speaking, the more frequent word or potential tokens appears in your training dataset, the less tokens it's going to end up being. Another way to reduce the cost is to use alternatives to LLMs, or at least alternatives to the expensive LLMs. You can use cheaper models. You can use all the way to model, early transformers model. BERT is one that we've had a lot of success with. It's great for several reasons. Only one of them is cost. BERT, there are a lot of variations, very successful ones. It's also relatively easy to train BERT for a specific task, and it's orders of magnitude cheaper. regex, another great alternative. Incredibles in terms of latency. It also helps with the accuracy. And at the end of the day, the cost of running a regex in relation to making an LLM request is topic modeling, a great alternative. Essentially, any external API which might perform the same task while not sending it to an LLM will normally be cheaper on a per basis cost. Now, I mentioned here cheaper models, but I do want you to take the cost of the model with a grain of salt. Things take time to develop, and you have to be forward thinking when you're undertaking a project. You don't decide to do a project today and deploy it tomorrow, and over time the cost of models decreases. In just a year, the cost of GPT has declined by over 90%, and I expect this to be the case in at least the year to come. Now, chunking. Chunking is how we ingest the relevant information that we're later going to be using. We're forced to choose how to chunk, and it really depends on a number of factors. It depends on your use case. It depends on the size of your context. It depends on which embedding model you're using, model performance. Chunking in small pieces, as you can see on the top example here, really doesn't capture the meaning, while chunking too large is also ineffective. If I chunk every word or every character, I'm not capturing any meaning, and if I'm chunking the entire document, I'm not capturing anything. Essentially, the goal is to chunk in a way that will be beneficial later when we retrieve these chunks in order to send them to the model. Now, there are different chunking strategies. The cheaper ones are normally also the ones that work not as well, where you just pick a fixed size. You get a little bit more expensive when you use things such as overlapping. And the more semantic meaning you capture and the more effective methods you use, the more expensive it's going to become. Just to give an example, Raptor, which is a very good strategy for chunking, recursively chunks and ranks and combines and summarizes the information recursively before actually indexing it. And obviously all of these cost money, and there's sometimes redundancy, intentional redundancy in retrieval, such as retrieving the parent chunk and stuff like that. But at the end of the day, on the bottom right, you can see a good example here where I use a recursive chunker, which is somewhere in the middle. It's still not chunking a fixed size and is able to relatively capture the semantic meaning, which we're not going to get into here, but semantic meaning a lot of the time correlates to paragraphs. Now, demo. This is a very good visualizer of how different chunking method looks like. It's by Greg Kramnot, who also has a very good YouTube channel, which I recommend you check out. This is just a text you can play around to see how different chunking strategies look. It's using the LangChain methods. These are by no means all of the different methods possible, but you'll be able to understand. So if I'm using a character splitter, fixed size, and I try to capture kind of the semantical meaning, it's relatively hard. Like I can capture the first paragraph, but then the second and third one get totally botched up. I can add like overlapping, which sort of will fix this, but again, not really. Obviously this doesn't work. It's a very rudimentary method. This one is already better. If I use the recursive character splitter, again with a one chunk size, it's not very good. But if I kind of play around with it, eventually I'll be able to capture a relatively good one. So it's not perfect overall, but it's a very good place to start. Great. Memory summarization. This is scenario specific. Obviously, a lot of the applications developed using LLMs are chatbots. And chatbots have this memory component where they continually drag the preceding part of the conversation along with us for context, so that we're able to do things such as the one you see on the right. I have an entire conversation about writing a blog post with ChatGPT, and at the end of the day, I just, as I would in a normal conversation, I'm able to say, do the first thing that you suggested, without dragging along the context, which kind of emulates a memory component. The ChatGPT would not know how to do this. Over time, this gets very expensive. You may not be writing a lot, but as you're familiar, unless constrained, ChatGPT gives very long answers. And if you're having a long conversation, it adds up. There are a lot of different strategies to deal with this. One of these is memory summarization, where before sending every input that you make, together with the context, it sends not the entire context, but the summarized context up until that point. If you're not doing this, is a very good strategy. It's also implemented in LangChain, so yeah, pretty easy to do. Caching, not specific to LLM applications. It works relatively well in terms of cost saving and performance on any different API. Here, caching means saving the pairs of the prompts and responses, and before querying any new prompt query, check cache for similar prompts that have been made before, and if the similar prompt exists, relay the response instead of going to the LLM all the way. There are two benefits for this. One is latency. You're going to get way faster answers for similar prompts, and cost, because again, you're not querying the LLM, and hitting a cache depends on where this cache is, but relatively speaking, it's almost zero. As with the previous slide and some of the other ones, LangChain again has an implementation of GPT cache. It has a few different strategies that you can implement cache. Let's see a small demo. So here I am working with LangChain. I'm working with GPT 3.5 Turbo, and I am using the cache. There are a lot of different strategies, some which already tie into existing vector databases solutions. You can use it using Redis. I'm using the in-memory because it's relatively simple. Okay, and what I want to showcase here is the fact that on the first time, first of all, it takes 1.2 seconds. And on the second time, it already takes, 600 micros, which is a huge save in terms of time, which is also important. And the cost is relatively zero, because first time I'm making the request to LLM and I'm paying per tokens, not a lot, but I'm still paying. And the second time I'm hitting the cache and I'm paying zero for the tokens. Next up is Finetune. Technically speaking, if you're using GPT 3.5 and then you fine tune, you're actually going to be paying more. The same applies to the rest of the providers because they have to save a specific component such as an adapter for your version, and it costs you more per token. However, a lot of the times you're able to take data or create synthetic data using a stronger model and then fine tune a cheaper model. Best example I can give is GPT-4 and then GPT 3.5 fine-tuned. You saw the table at the beginning. Between 4 and 3.5 fine-tuned, we saved more than 95% of the cost. So it's worth it. What you have to do in order to fine-tune is collect the data, either the queries and the answers or the queries and the answers and the feedback. That's the plus and a minus sign that we have on most chat applications, definitely the OpenAI ChatGPT one. Then we use that in order to fine-tune the models. Next up is batching. Batching is not exactly a way to save cost. It's first and foremost a way to increase the throughput. However, there can be benefits if the context is shared between a few queries. That way you're sending several queries together with the same context, and that getting amortized over several queries equates to less cost instead of sending each query with the same exact context. But that's more a question of like, are you able to reliably do that? The second is if we're running in a self-hosted scenario, throughput equates to saving costs, because assuming you're constantly using the infrastructure, gaining more throughput from the same infrastructure will equate for cost saving. Another method, and I'll admit I do not have experience with this one, but as I was preparing for this session, as we always do, I check to see if anything has changed or if new things have come out that were not or have not used in production. WebLLM is one of those, and you probably can get from the name that it's a way to load a model in the user's browser. And the obvious benefit is that you're not sending tokens to OpenAI. You're not paying the cost of that. Instead, the compute cost will be on the user. Next up, one of my favorite methods, which you should definitely check out, is prompt compression. For those of you who remember the table back in the beginning of the talk, that was kind of the last step, but it can be applied to everything. It's not that you have to use Mistral 7B before you can think about prompt compression. There are several ways to do prompt compression. An easy one using a Python library such as GPT trim is a rather naive approach. The problem with that is that it does not necessarily keep the semantical meaning, which is bad. LLM Lingua is a better method. It was released by Microsoft. By now there's already LLM Lingua 2, which is what I use in the demo. We'll see this. It's great. There are a lot of insights from the paper, 9 if to be exact. I cherry picked 4, which I think are very interesting here. First of all, natural language is redundant and the amount of information in it varies. LLM can actually understand the compressed prompt, meaning you don't have to do this like back and forth of sending it over compressed and then opening it, stuff that you might have imagined if you're thinking about a compressed zip file. GPT-4 can recover all key information from compressed prompt, which is great, and also like an emergent ability. Last but not least, prompt compression can be formulated as a token classification problem and accomplished by a BERT-sized model. Anytime you can do something with a BERT-sized model as opposed to an LLM, that's a plus. Now, on the right, you see all kinds of types of abbreviations that can be applied. And at the end of the day, this one, I think I took it from Frugal GPT, which we'll be discussing at the end of the talk. This paper achieved 98.3 compression. Compression equates cost saving. If you're compressing by 98%, you're saving 98% of the cost. Let's see the next demo. Okay, here we have Here we're making a request without any compression to GPT 3.5, and you see that the answer is the agenda item resolution 31669 is about Fair House Act. Then we go through using LLM Lingua to compress the prompt, and there are a couple of things that we can control here, but the most important one is the compression rate. We run the same query again with the compressed prompt. Everything else stays exactly the same, and point in case the result is similar, resolution 31669 and the Fair Housing Act. And does this mean that, is this a proof that compression works? No, at a whole compression works. I recommend that you read the paper. I recommend that you also do some stuff to test it on a larger scale than what I'm showcasing here, but it works, it's easy to implement, and it's one of the best ways to save cost. Next up is routing. Now, routing can be done in a couple of different ways or a couple of different strategies. Different strategies kind of have different constraints, but at the end of the day, the approach or the goal that you're aiming is finding the minimum viable model, or the cheapest model that will give you the best answer. How do you do this? Different methods for doing this, but at the end of the day, when you boil it boils down into two. You have some kind of component which estimates the model output quality, and then you route to the selected LLM. There are two papers mentioned here, which I'll also link in the comments. One is Hugging GPT from last year. This paper showcased how to have an LLM plan what it's about to do in different steps, figure out for different steps what is the best task-specific model to perform that step, and then it will route the different steps into different models available on Hugging Face. On the bottom, it's CodeQPT. This paper optimizes both cost and performance by estimating the output on different sections of the query, but also optimizing for a budget. Cascading. In fact, this is the last method that we'll be discussing. Cascading means you have a prompt or a query with context that you'd like to send to a model, and then you start escalating. You start from the cheapest alternative that you have. Here I've just listed three. First one using BERT, second is Mistral and GPT-4, which are more expensive and more costly as we progress, also more performant. But again, remember, the objective here is not to send everything to the most performant model, because that's GPT-4 and it's also the most expensive model. We start by querying a simple model or a simple method. This could also have been regex or an external taxonomy or an API. After each section, we try to verify if it's enough, if it's good enough, if we're happy with the response. If yes, we take the answer and move on. If not, we escalate to the more expensive model. And you can build much more robust pipelines and have many more steps in this cascading. Up until now, we discussed a good chunk of methods that you can use in order to optimize cost. I'd like to refer you to a good paper from Stanford, which is called Frugal GPT. Frugal, obviously from the monetization concept, where they try to save money when they're using GPT models. They do three things here at a high level. First of all, they do prompt compression. They also do LLM approximation, which is trying to figure out what is the cheapest yet performant LLM that they can send it to. And last but not least, they implement model cascading. Is it a must? No, it's not a must. Similar to the talk that we have on the channel about hallucinations, there are a lot of strategies and methods for dealing with hallucinations, similar to how there are for reducing cost. This is a cost value kind of discussion. You need to be familiar with the methods, and you need to choose the one that makes sense for you. First of all, not every scenario benefits the same from all of these methods, and some of these are really costly to implement, at least until there'll be some kind of abstraction through LangChain or Llama Index or a different third party library that might come to play. Thank you very much for joining. I hope this talk contributed in some way to something that you're doing right now, or maybe doing with LLMs in production. If you have any questions, feel free to reach out to us. We have a website, reachlatent.com. We also have an email, which is info@reachlatent.com. This goes directly to my mailbox. I'm happy to try and help you out. As always, thank you for watching. Like, share, subscribe to be notified on more videos. It really helps us out. And I'll see you again next week. Thank you very much.